Okay, so now we are recording again, and I just restart where I started 1 hour ago. So the last class, we started to index X-ray diffraction pattern, and we determined the HKL values, and we also determined the lattice parameters. Okay, for the example of cubic unit cells. So in these examples, everything was very simple because a phenomenon called systematic absences did not occur. So what does systematic absence mean? Systematic absence means that under certain circumstances, not all possible reflection plane can be observed in an X-ray diffraction pattern. Under circumstances, there can be additional destructive interferences between diffracted X-rays that make the diffracted X-ray for a particular lattice plane not observable. In particular, that can happen under two circumstances. The first case is that we have not a primitive lattice, like in our previous examples of last class, but a centered lattice. And the second possibility is that we have symmetry elements that contain translational symmetry. Namely, we have either screw axes or glide planes or both. So let us first look at systematic absences due to centering. Okay, we have learned about centering before. We can have I centering, F centering, C centering, B centering, and A centering of a unit cell. So now when an I-centered unit cell is present, then you will only observe those peaks where H plus K plus L is an even number. Okay, so for example, you could observe a 1, 1, 0 peak because 1 plus 1 plus 0 is 2, but we could not observe a 1, 1, 1 peak because 1 plus 1 plus 1 would be equal to 3, which is an odd number. Okay? So if you have an F-centered cell, then you can only observe the peaks for which HKL are either all even or all odd. So for instance, you can observe a 2, 2, 2, okay, a 2, 2, 4, a 4, 4, 8. You could also observe a 1, 1, 1, a 1, 1, 3, or a 1, 3, 5. Okay, but you could not observe, for instance, a 1, 2, 3 peak. All right, so if you have a C-centered unit cell, then H plus K must always be an even number. Okay, when we have a B-centered cell, then H plus L must always be an even number, otherwise we cannot observe peak. And when we have an A-centered cell, then K plus L has to be an even number, otherwise our X-ray, diffracted X-ray will be absent. Okay, so now in addition to that, you can have systematic absences due to screw axes and glide planes. So for instance, when you have a 2, 1 screw axis which runs along A, then for H00 peaks, okay, peaks of the types H00, H must be an even number. That means that you can observe a 200, a 400, a 600, an 800, but you couldn't observe a 300. All right. So when the 2, 1 is parallel to B, then for peaks of the type 0K0, K would have to be an even number. if our 2-1 screw axis was parallel to C, then for the peaks of the type 0, 0, L, L would have to be an even number. Okay? So for instance, when we have a 3-1 axis parallel to C, then for peaks of the type 0, 0, L, L would have to be 3 times an integer number. So we would be able to see the 003, the 006, the 009, okay, and so on. But we would not be able to see a 002, for example, or a 004 or a 005. Yeah? So for a 4-1 screw axis parallel to C, for instance, peaks of the type 00L would need to fulfill the condition L is equal to 4n, whereby n again is an integer number. So we would be able to see 004, 008, 0012, and so forth, but nothing else. So glide planes can also cause systematic absences. So for instance, when you have an A glide plane perpendicular to the C direction, then for peaks of the type HK0, H would have to be an even number. Okay, so you could have, for instance, a 2, 1, 0 or a 2, 2, 0, but it couldn't have a 3, 2, 0, for instance. So for a B glide plane perpendicular to C, the HK0 peaks would only be allowed when K is an even number. For an N glide plane perpendicular to C, peaks of the types HK0 are only allowed when H plus K is an even number. Okay, so for instance, a 1, 1, 0 would be allowed because 1 plus 1 is equal to 2, but a 2, 1, 0 would not be allowed because 2 plus 1 would be odd. Okay, now when we have an A glide plane perpendicular to B, yes, please speak. 2 participants raised hands, so I don't know exactly who, but if you
Mohammed, I think you were first.
So who was first? Who wants to speak first?
I think Mohammed was. You there?
No, I think it's shown the previous time I raised hand. I don't have any question.
Okay, okay.
Okay. Just a quick question for the glide planes then. So for an N glide, something like a 220, now that would apply to A and B as well as N. So is it always the highest order? Would that then be only an N glide plane?
I'm not sure if I understand your question. Can you say this again?
Sure. So say a 220 where H is even, K is even, but they also add up to be an even number.
Yeah.
Is it only an N glide plane or is it an AB and an N?
In A, B, and N.
So if it's 220, it fits the things necessary. So because H is even, it would fit to be an A glide. Because K is even, it fits to be a B glide.
Yeah. So based on one reflection alone, you could not make the decision whether it belongs to N or A. You would always have to look at a series of reflections, okay, in order to decide if it belongs to an A or an N. Okay, so for instance, if it's an A glide, okay, the only condition that H is an even number. Okay, so K can be anything. Okay, so you would observe any K. 1, 2, 3, 4, 5, 6, 7, or so, and so on. Okay, but for this one here, h plus k must be an even number. So that is different. So still, yeah, you could have any value of k. Okay, but when you have an uneven number of k, for instance, okay, like 3, your h value must also be odd. Okay, so that is inconsistent with the condition for the glide plane A, because in the glide plane A, h also always has to be even. So this is how you can distinguish an n from an A. But by looking at one reflection alone, you may not be able to make the case. You have to look at the entire series of your observed reflections, and your condition, your reflection condition, your systematic absences must hold true without an exception. Okay, if you find one exception, then that must mean that systematic absence is not there. Therefore, it helps you when you have actually many X-ray diffraction peaks, because then you have many lattice planes you look at, and the chance that you actually overlook a violation of the systematic absence becomes smaller. Does that answer the question?
I think so. So basically, if we were asked something like that, like if you have a 2-2-0 plane, you know, what glide plane does that relate to? It would be you can't tell. You would need more information.
Yeah, based on from one you couldn't tell. You could say, well, it can be either this or that or that. It rules already out some cases, but not necessarily all other cases.
Okay. All right. So it's not specific. All right. Thank you.
All right. Okay, where did we stop? I think we stopped with the A glide plane perpendicular to B. Then you look actually at the H0L peaks, and again the condition that H has to be even. So for a C glide plane perpendicular to B, we look again at H0L peaks, but they are only allowed when L is equal to even. And for N glide plane perpendicular to B, H0L peaks are only allowed when H plus L is an even number. Okay, so you see that these are of course only examples. We can have more screw axes. Here we only look at a few examples, and we can also have more examples of glide planes. Okay, so I would not expect you actually to memorize these conditions here, but I think you should know the conditions for the centering, just because they are very few and they relate to the very basic property of lattices to be centered. Okay, but don't memorize this, but I would expect that you know the conditions shown on the slide before. Okay, so now I said that the systematic absences can make indexing of X-ray diffraction patterns more tricky, and I want to show you this here by one example. So you see here again an example of an X-ray diffraction pattern. You see that under those angles here, 2 theta angles here, we observe peaks. Okay, our radiation is again copper radiation. Yes, Tom.
Oh no, I'm sorry. I was just taking my hand down from before.
All right. So certainly, like in the previous class, we can determine the sinus square theta values and multiply this by 1,000. Then that gives this series of values here. So again, we would have to find a common factor by which we can divide all these values to give integer numbers, okay, for all these values. So now in the previous examples from last class, we said that, well, the first peak would be associated with the 1, 0, 0 plane. Therefore, 1 square plus 0 square plus 0 square would be 1. So our integer number would be 1. And because of that, our common factor would just be identical to the first sinus square theta times 1000 value. Okay? So this worked for our previous examples, but you see that it actually doesn't work for this example. Okay? So 47.84 divided by 47.84, yes, that gives an integer number, which is 1. But you can see that 63.87 over 47.84 obviously does not give an integer number. So that implies that 47.84 is, in this case, not the common factor. And that also implies that there must be some sort of systematic absence present, because obviously we cannot observe the 1, 0, 0 lattice plane. Okay, so what you can do in this case is that you systematically go to lattice planes with higher d-spacing. So you could, for instance, guess that your first peak is associated with the 1, 1, 0 lattice plane. All right, so if this is the case, then because 1 square plus 1 square plus 0 square is 2, your common factor would be 47.84 over 2. Okay? If you calculated that and used it to determine the other integer values, from these numbers here, you would find again that it will fail. Okay? So that means that also the 1, 1, 0 lattice plane must be systematically absent. Okay, now we can go to the next lattice plane, the 1, 1, 1 lattice plane. So now 1 square plus 1 square plus 1 square is equal to 3. So therefore our common factor would be 47.84 over 3. So what is that? So that is 15.94. And when you use this factor, you will find that all of a sudden everything works. Okay? So 47.84 over 15.94 is equal to 3. 63.87 over 15.94 is equal to 4. 128.45 divided by 15.94 is equal to 8. Then 177.40 over the common factor gives 11. 193.82 over the factor gives 12. 260.08 over 15.94 gives 16. 310.45 over 15.94 gives 19. And 327.37 over 15.94 gives 20. Okay, see, works great. All right, so now we can again calculate our lattice constant from our common factor. Okay, we have previously seen that lambda square over 4a is equal to our common factor divided by 1000. So it is in this case 0.04784 over 3, okay, or 15.94 over divided by 1000. All right, so because we know lambda, we can calculate a, which would be in this case 6.1 angstroms. Okay. So now we already know that we have to have some sort of systematic absence. Now you can actually next check the systematic absences due to centering and see if your unit cell is somehow centered. So now analyze now we can determine the HKL values from these integer numbers. So the integer number of 3 can only be explained by h is equal to 1, k is equal to 1, L is equal to 1. 4 must be associated with 2, 0, 0. 8 must be associated by 2, 2, 0. 11 by 3, 1, 1. 12 by 2, 2, 2. 16 by 4, 0, 0. 19 by 3, 3, 1. And 20 by 4, 2, 0. Okay, you see in this case, all HKL values actually are unambiguous. So now you can see which type of centering does that reflection condition suit. Okay? And you see that in this case, it's the F centering, because you see that either all HKL values are odd or all HKL values are even, whereby 0 counts as even in this case. Okay, so here they are all odd, here they are all even, here they are all even, here they are all odd, here they are all even, here they are all even, here they are all odd, and here they are all even again. All right, so there we can be fairly certain that we have F center. We have an F-centered unit cell with a lattice constant of 6.1 angstroms. All right. So now we have determined basically our lattice and our lattice constant, but we actually do not know yet the positions of the atoms within our unit cell. Okay, remember I told you previously that atoms do not necessarily need to sit off lattice points. They can in principle sit at any point within the unit cell. The only requirement is that the atom positions follow the symmetry of the crystal. So in order to derive the absolute atom positions within the unit cell, we must now look at the intensity of our diffracted X-rays. Not only the 2 theta values are relevant, but also the intensities. Only with the help of the intensities we can determine the atom positions. So now the intensity of a diffracted X-ray associated with Miller indices HKL is given the following way. It's the so-called structure factor square times the Lorentz factor times the polarization factor times what is called the temperature factor. So all these factors influence the intensity. Now the coordinates of the atoms are within the so-called structure factor, hence the name structure factor. The Lorentz factor is actually a factor which is due to the angle under which the lattice point in the reciprocal lattice enters the Ewald sphere. Actually, when the angle is smaller, the lattice point enters under a smaller angle and therefore remains somewhat longer on the surface of the Ewald sphere in comparison to higher angles. And that influences the intensity because the longer a lattice point in the reciprocal space stays on the surface of the Ewald sphere, the higher the intensity will be. So the Lorentz factor takes that effect into the account. So now the polarization factor we have actually discussed on a previous class. So as the X-rays get diffracted, they get polarized to some extent, and because of that, the intensities tend to decline at higher diffraction angles. So last but not least, we have the temperature factor, and the temperature factor accounts for dislocation of the atoms from their equilibrium positions due to temperature. So the atoms, they do not sit completely fixated on their positions within the crystal. Due to temperature, they wobble around. a little bit their equilibrium positions. Okay, that also has an influence on the intensity of the measured X-rays, and that's accounted for by the temperature factor. Okay, so now I said previously that the structure factor contains the atom coordinate. Therefore, in the following, we will look at the structure factor in more detail. So you can see from this formula here how it contains the absolute atom coordinates. So the structure factor is actually the sum of the atomic form factors over all the atoms, J, okay, times this exponential term here, which contains the atom coordinates X, Y, and Z. Now at first glance, it looks like it's very easy to extract the atom positions X, Y, and Z from the intensities because there's a direct relationship between the intensities and the structure factor. However, there's one very unfortunate complication, which is that the intensity is actually the square of the structure factor. And that arises ambiguity with regard to the atom positions, okay? So for instance, the structure factor could have the value of -2, okay? Then -2 times -2 square, that gives 4, okay? And 4 would be our intensity. But the structure factor could also have the value of +2, because +2 times +2, that also gives 4, okay? So this gives rise to a problem which is called the phase problem, okay? So actually, in order to determine our atom positions within the crystal structure, we would need not only the intensity of our diffracted X-ray, but also the phase. And unfortunately, the phase cannot be experimentally determined, okay? So therefore, the determination of crystal structures from the intensity of X-rays is not straightforward due to the phase problem. This is also, the phase problem is also illustrated here. So this formula here shows you the electron density function, which is nothing else basically but the, X-ray, the atom positions, because the presence of the atoms at a position in the unit cell will give a peak in the electron density function, because where the atoms are, there are also the electrons, okay? And an X-ray diffraction experiment measures the, electron density because the X-rays get diffracted at the electrons. We discussed this also previously. All right. So this is the electron density function within the unit cell, which is equal to this term here. So it's 1 over the volume of the unit cell times the sum over the HKA values of, all the absolute values of the structure factor, okay, times the cosinus of cosinus pi times hx plus ky plus lz minus the phase, okay? So unfortunately, that phase, this term, cannot be experimentally determined, giving a rise to the phase problem. So now how can you solve that phase problem? And there are different methods how to go around the phase problem. There are actually two major methods. One is called the Patternson method. It's also called the heavy atom method. And the other method is the direct method. So in the context of this class, I will only focus on the Patternson method just because it's much more straightforward understand. So, so Patternson, Arthur Patternson, noted that while the electron density function requires the knowledge of the phase of the diffracted X-rays, a related function named after him, the Patternson function, actually does not. So you see here the Patternson function, and you see it's very similar to the electron density function. It's also 1 over V times the structure factor, whereby now we have to look at the square of the structure factor, which we can now directly correlate to the intensity of our diffracted X-rays. Yeah. Times the cosine is 2 pi times HU times KV times LW. So now U, V, and W are coordinates in the Patternson space. Yeah, and these coordinates are related to the coordinates x, y, z in the actual real space the following way. They just represent differences between the coordinates of two atoms. Okay, so U is defined as the difference between two x coordinates of two atoms in the crystals. Okay, V is defined as the difference between two y coordinates of two atoms in the crystal, and W is defined as the difference between two z coordinates within the crystal. Okay, so now at first glance, it looks like, well, the Patternson function doesn't help you much, because we are not really interested in the knowledge of atom distances within the crystal, but we are interested to know the absolute position of the atoms in the crystal. Yes.
I want to know, like, when you say x1 and x2 are the positions of the two different atoms, how do we know which two atoms?
The atoms of the same type. Okay.
For example, in FCC, if we consider two corner atoms, there are like 8 corner atoms in one unit cell. Which two should we consider?
Well, all of them. All of them. Okay? All of them, because all of them have a distance, relative distance to each other. Yeah? I mean, those on the corners, they have a distance of 1 unit cell parameter to each other. And those ones, those ones on a corner, on a face center, they have a different distance to each other. Okay? So each distance would correlate to a value U. Yeah? All right.
Okay, thanks.
Good. Then at first glance, it doesn't look like this helps you much, but actually a student of Arthur Patternson, his name is David Harker, found that with the help of symmetry within the crystal, we can derive the absolute positions from these relative positions using what is named after him, Harker lines and Harker planes. Okay? So for instance, we have a crystal in the space group PM. Okay? Then we can look into the international tables for crystallography, and we'll find that in the space group PM, when we have an atom on the general positions X, Y, and Z, then due to the presence of this mirror plane, that same atom must also be present on the coordinates X minus Y and Z. Okay? Because in this case, we reflect at the coordinate Y, which turns Y into minus Y. In our lattice plane, sorry, not lattice plane, mirror plane, in this case, the XZ plane. So now what we can do is to subtract these coordinates from each other, yeah? Just like the Patternson function does. And then we will find that x minus x is equal to 0, y minus minus y is 2y, and z minus z is 0. Now you see that this defines a line because we have only y as the variable, while x and z are fixed values, in this case 0. So if we were in the space group P21, for instance, then for each atom on a general position, x, y, and z, we would have to find the same atom on the position minus x minus a half plus y and minus z. That is due to the presence of the 2, 1 screw axis. Okay. So now we can subtract these two values from each other. So x minus minus x, that gives 2x, y minus a half minus y, well, that gives a half, and z minus minus z, so that gives 2z. You see that this defines a plane, in this case an xz plane, okay, because x is variable and z is variable, but y is being fixed. All right, now you can use Harker lines and Harker planes in order to determine absolute atom positions from relative atom positions. And I want to show you that by an example. All right, so let's say we have measured a crystal, in this case of this composition here. So this is zinc dicyanide times a solvent, which is included in the crystal. It's DMP, and DMP stands for dimethylphenantoline. So we can determine from our X-ray diffraction pattern already that we are in the space group P21 over C. Okay. We can determine the space group from the unit cell plus the systematic absences that give us information about the glide planes, yeah, in this case C, and the screw axes, which in this case a 2-1 screw axis. All right. We expect that we have 4 formula units within our unit cell because of density arguments. Yeah. So now we can calculate our Patternson function from the measured intensities, X-ray intensities. And you will find that this Patternson function has maxima at certain positions, U, V, and W. Okay. So the most intense maximum is at the position 0, 0, 0 in this case. The second most intense one is at the position 0.5, 0.5, 0.45. The third most intensive position, peak is at 0, 0.05, 0.5. The fourth most intense one is at 0.51, 0.45, and 0.95. And the fifth most intensive one is 0.26 at 0.92 and at 0.14. So now you make the following guess and say that these peaks are most likely associated with the position of the heaviest atom. Therefore, this Patternson method is also sometimes called the heavy atom method. That is because X-rays are most strongly diffracted at the atoms that are the heaviest. That is because X-rays are diffracted electrons, and the heaviest atoms have just the most electrons. All right, so we'll make a guess that the position of the zinc atom will be associated with the most intense peak in the Patternson function. So now we can use Harker lines and Harker planes to derive exact atom positions. And we can do this the following way. So we know that we are in the space group P21 over C. Okay, we can look into the international tables for crystallography and find that for a general position, X, Y, and Z, due to the presence of the symmetry elements 2, 1, and C, that same atom, and we assume that this is now the zinc atom, is also located at the positions minus X half plus Y half minus Z, minus X minus Y minus V, Z, and X a half minus Y a half plus Z. So this position is created due to an inversion center present in the unit cell. This position is created because of the 2-1 screw axis, and this position here is created because of the C glide plane. All right, so now we can again calculate Harker positions from these positions here. So to do so, we subtract these 3 positions from the original position. So let's first subtract this position from that position. Then we have X minus minus X, that gives 2X. Y minus a half minus Y, so that gives minus a half. And Z minus a half minus minus Y, so that gives minus a half plus 2Z. Sorry, Z minus a half minus minus Z, so that gives minus a half plus 2Z. So now we see that this is a Harker plane because X and Z are variable while Y is actually fixed. So next we subtract this coordinate from that coordinate, and X minus minus X, that gives 2X, Y minus minus Y, so that gives 2Y, and Z minus minus Z, that gives 2Z. So last but not least, we subtract this from this coordinate. So X minus X, that gives 0, Y minus a half, minus minus Y, then it gives minus a half plus 2Y, and Z minus a half minus Y, so that gives minus a half. So you see that this defines a Harker line. Okay? So that position here is neither a Harker line nor a Harker plane, therefore it's actually not useful for us, but these two are useful. All right, so we can slightly rewrite these positions the following way. We can always translate according to a 4-lattice parameter. Okay, then the resulting position is equivalent to the original position because of the presence of translational symmetry. So if we put ourselves on the position minus a half and translate, well, 1 unit cell parameter into Y direction, our position will be plus a half, but these two positions will be equivalent. So we can also do this with this position here. If we now translate by a 4-lattice parameter into Z direction, then minus a half plus 1 will be plus a half. It should be equivalent to minus a half. So then we eliminate these two negative values here, make them positive values. And that is useful because now we can relate these values to the positions, peak positions in the Patternson function. Okay, so we can first look at the Harker plane here, 2x a half, 2z minus a half. And according to that, well, x can be variable, z can be variable, but y can actually not. So that y, because it has been derived from a subtraction of two y's, is now actually a v, yeah, in the Patternson space. So v has to be equal to a half. So now we can look back and see if there's any peak in which v is a half. And in this case, luckily, this is only the case for one of the 5 peaks here, is actually the second one. So we therefore can say the following: if this peak here is associated with that Harker plane, okay, then 2x must be associated with the u value for that peak, and 2z minus a half must be associated with the w value of this peak. So according to this, 2x must be equal to 0.5. That is, for this second peak here, u is 0.5. And 2z minus a half must be equal to 0.45, because now for the second peak, w is 0.45. All right. Now we can easily solve this equation for x, then x is equal to 0.25. And we can solve this equation for z, which is equal to 0.447. Okay, now you see that magically we have found the x and the z positions for our zinc atom within the unit cell. So we do not know yet the y position, but for finding the y position, we can use the Harker line. Okay. So the Harker line has the form 0 minus a half plus 2y a half. Okay. So now this Harker line can be associated with the peak number 3, because for the peak number 3, you see that u is equal to 0 and w is equal to 0.5. Okay, so that matches that 0 and that's 0.5 here. Okay, now according to that, minus a half plus 2y must be equal to the value of v for that respective peak, which is in this case 0.05. Okay, now we can say that, well, minus a half plus 2y must be equal to 0.05. Okay, and we can just solve that for y, and then we have found our position y of our zinc atom, which is equal to 0.27. Okay, now we have found all the positions of our zinc atom. Okay, so now we can further verify that this solution is true by checking if also the other position, the Patternson function, can be correlated to these positions here. Okay, so now you can see that this works this does not work for peak number 4. So so for the position 2x, 2y, 2z, we would have to find a peak 2 times 0.25, 2 times 0.27, 2 times 0.47, which is 0.50, 0.54, and 0.94. So this here should correlate to a peak in the Patternson map. So however, when we look, then we see that peak number 4 comes close to that, but it's actually not quite right. So the U values and the W values are close to 0.50 and 0.94, so we can attribute the differences due to experimental error, but 0.54 is too far away from 0.45. However, also in the Patternson space, there is symmetry. Okay, it is just that the translational symmetry elements are being removed. So for any position UVW, due to the inversion center, we also have an equivalent position U minus VW. Okay. Now for the 2-1 axis, basically we remove the translation, and then basically UVW becomes minus U minus W. And if we remove the translation from the C glide plane, then it becomes simple mirror plane. Okay, and UVW becomes U minus VW. Okay, so now when we turn 0.54 into minus 0.54, so V becomes minus V, and translate by a full lattice parameter, which we can also do, then 0.54 plus 1, that gives, well, 0.46. So, sorry, slightly wrong. So 0.54 becomes minus 0.54. When I add 1 to that, then it becomes 0.46. And now 0.46 adequately matches that 0.45. And we have actually identified or associated the last Harker position, which is in this case 2x, 2y, and 2z, also with a peak in the Patternson map. All right. So now we have further verified that that position here, 0.25, 0.27, and 0.47 is the correct position of the zinc atom. All right, so I see that we are already over the time, so I can stop the recording now, but I'm still happy to answer questions.